and welcome back to the Barbie Bungee podcast. I'm your host, Auveen Hajar, and today we have something very special for you. We have created an application that is capable of determining how far down a passenger will go on Oaks Amusement Park's newest ride, the Barbie Bungee Adventure. Our application is capable of determining many forces involved in the ride, the elastic, kinetic, and potential energy at multiple points during the ride, and overall a lot of cool stuff. But before we introduce you to our app, let's discuss some of the science of our application. I want to introduce you to two very special guests, Ethan Durham and Rahul Shah. Let's start with Ethan. Ethan, how are you today?
Thanks, Auveen. I'm doing great. First, let's talk a bit about the physics of bungee jumping. Bungee jumping involves several forces as well as different kinds of energies. These energy types are the gravitational energy, how much energy you have at each point of the jump due to gravity, the kinetic energy, how much energy you have based on your current velocity, and finally the elastic energy, how much energy is contained in the bungee cord while stretching. Throughout the whole jump, from top to bottom, the total amount of energy must remain the same. This means that the total amount of energy at the top of the jump is equal to the total amount of energy at the bottom. This is because energy is conserved. Energy is not created nor destroyed, but rather transformed into other energies, meaning that the total energy in any given system must always remain the same, the system in this case being the string, bungee cord, and the jumper.
Whoa, thanks Ethan. That sounds pretty cool. Would you also like to talk a little bit about how you calculate the gravitational potential energy at the top and the elastic energy at the bottom? I think our fans would actually enjoy hearing about it.
Of course, Auveen. To start, in order to calculate the gravitational potential energy, you need to know the mass of the jumper as well as the total height of the jump, that is, the distance you want the jumper to travel. This specific distance can be calculated by subtracting the safety margin from the height of the jumper at the top. Once found, the gravitational potential energy can be accurately predicted through the gravitational potential energy formula, being Eg equals mass times height times the gravity constant of 9.8. Keep in mind, the gravitational potential energy also represents the total energy of the system because the velocity is zero, so there's no kinetic energy, and the cord has not stretched yet, meaning there's also no elastic energy. At the bottom of the jump, the velocity of the jumper must be zero, which means that the kinetic energy is zero, and since the jumper is at the bottom, the height is zero, and therefore the gravitational potential energy will be zero. Because of the conservation of energy, the total energy must remain the same, and therefore the elastic energy at the bottom of the jump must equal the gravitational energy at the top of the jump.
Awesome! Sounds fun, and I'm glad that you could share this information. Let's also talk a little bit about why we have safety zones. In the case of bungee jumping, there's always the possibility of an outside force acting on the jumper, the cord, or the added string. An unexpected force could change the results of the jump and lead to someone dying because they hit the ground. Safety zones are designed for the bungee jumper's ride operator to plan as though the top of the safety zone were the ground. This way, safety zones are able to protect people in case something goes wrong. But anyways, let's get to our second guest and hear what he has to say. Rahul, how are you doing today?
I'm doing well, thanks Auveen. I want to talk a little bit about the relationship between the force versus stretch of a bungee cord. Bungee cords all stretch and they stretch different amounts based on the amount of force applied. This can be mathematically modeled as F equals Kx, where F is the amount of force applied, K is the K constant of a string, or bungee cord in this case, and X is how much it actually stretches in meters. The K constant is a value that represents how easy or hard it is to stretch the string, or the bungee cord. The force applied is proportional to the stretch, meaning the more force applied, the more the bungee cord will stretch.
Interesting. But before we leave today, I have one last question for you. How are mass, K constant, and stretch related to each other during a bungee jump?
I'm glad you asked. The mass of the Barbie and the K constant of the bungee cord both affect how much the cord will stretch and the total vertical distance of the cord. Because of the conservation of energy and what Ethan talked about earlier, how the energy of the Barbie at the top must equal the energy at the bottom, We can equate the two formulas for gravitational potential energy and elastic energy, and then shuffle them around to solve for the total stretch. And what this shows is that an increase in the mass will change the total stretch proportionally to the change of the mass, while increasing the k constant will change the total distance stretched inversely.
Great! That's all the time that we have for today, so thank you to both of you. Have a great day.